So now we are ready to talk about unit cells for pure metals. They have the following possible tree structure. They are either simple cubic, body-centered, or face-centered. If you're simple cubic, at each corner of that unit cell you have one atom. But really, how many atoms you have for one cage like this, one unit cell like this? Now this is a little bit more accurate picture. The atoms are touching each other at the surface. Now this is what happens. You have 1, 2, 3, 4, 5, 6, 7, and 8 corners. Now each corner contains 1/8 of an atom within that unit cell. So you have 8 times 1/8, which is equal to 1 atom per unit cell. And that is true for simple cubic. And that's an important piece of information because eventually we use it for sake of calculations of the different structures. Now if you're body-centered, within the cube you also have 1 atom trapped. So now you have more atoms per unit cell. You still have also 8 atoms at each corner. Now this is then again more accurate picture. There are voids. The surface atoms are really not touching each other, so you have a gap here and there is 1 atom inside. But if you want to calculate how many atoms you have per unit cell, you have 1, 2, 3, 4, 5, 6, 7, 8 corners, 8 times 1/8 of an atom within, plus 1 whole atom inside, plus 1. So that is 1 plus 1. There are 2 atoms per unit cell for body-centered, and body-centered is sometimes shown as BCC, body-centered cube. Now face-centered cube is, you also have on each faces of this cube you have also an atom, but inside the cell you are really sharing half of that atom. The other half is shared with the neighboring. So if you want to calculate how many atoms you have per unit cell, this has the most actually. It has then again 8 corners of 1/8 of an atom, plus you also have 6 faces, 1, 2, 3 in back, 4, 5, 6 faces that has half of an atom within the cell. So 6 times half, you have 1 plus 3. This has 4 atoms, the most per unit cell. This is a crucial piece of information that you either have to memorize or remember how to do it. So face-centered contains 4 atoms per unit cell, body-centered contains 2 atoms per unit cell, and simple cubic simply has 1 atom. The next slide is redundancy of the same thing, number of atoms per unit cells. Then this is the simple, this is body-centered, has 2, this is face-centered that has 4 atoms per unit cell. Now another piece of information is you also need to relate the radius of each atom to the side of that unit cell. So if this is a radius of 1 atom from this to here, I want to somehow relate it to the distance here or the sides. Now the next slide, instead of D for the distance of the unit cell, I have A, but let's see how those calculations are done. And then again, you either memorize it or remember it, but it's an important piece of information. The simple cube is actually the simplest. Now this is A, the distance of each side. The same thing goes for this. This is also A. Now there are 2 atoms touching each other, so this is a radius of 1 and this is the radius of the other one. So the distance of the side is actually 2 times the radius. If you look at a body-centered cube, this is what happens. Now you have one side here, you have another side here, A, and this is Pythagorean theorem, a squared plus a squared is equal to hypotenuse squared, so b squared is equals to a squared times a squared. Now this is another triangle within that you have now the picture doesn't give you the right angle to look at, but this a squared plus b squared should equal to c squared. then what you can do is plug them in and say, if b squared was a squared plus a squared, b squared plus a squared should equal 3a squared. Then c, which is, you have now one atom inside, and on the edges you have, so from here to here this is r, but then you have another r here, you have r here, and you have r here. So c, hypotenuse, is really 4 radiuses, so c should equal to square root of 3 times a, the distance, the side, so a could be written as 4r over square root of 3. Now this is a little bit difficult, so collect it, remember it, or be able to work it out. Face centered is also easily calculated. Now you have one side and another side, which is a, and hypotenuse is, then again you have one r here. This is diameter divided by 2, so you have r radiuses, and you have the fourth r. So b is equal to 4r, that's given from this. And if you squared a squared plus the other side, a squared should equal hypotenuse squared b squared. So b squared is 2a squared. Instead of b, put 4r, so 16r squared is equal to 2a squared. Finally, a is square root of 8 times r for face-centered cube. These are important piece of information. The last slide for this unit, I'm going to apply them to calculate density of pure solids, or we have to decide what is the structure with given information. So remember this, we are going to apply it in the next slide.